today we're going to be talking about rates of change. Basically, all this is some applications of all that derivative work that we've been working on. So, average rate of change. So remember, average rate of change of a function over an interval is the slope of the line through those 2 points. So f of b minus f of a all over b minus a. So this is our average rate. And then we have instantaneous. So the instantaneous, I always struggle with that word, rate of change. Remember what that is? That's our derivative of a function. So an application that we're going to be using a lot is particle motion. So motion of a particle walking up and down a number line, essentially. That's what we're going to be doing. A particle walking up and down a number line. So imagine you're standing on the trail, the Iron Horse Trail, you just walk up and down. So I have a function s that gives the position. So our position function is typically, we're going to call s of t. Of an object is called the position function. Okay, so s of t. Over a period of time t, the object changes its position by the change in time. So my starting point plus some change in time, so 3 seconds later, minus where I started. And then we have a familiar formula, rate equals distance over time. The average velocity is given by change in distance over change in time. Well, what is this? Remember, that's a fancy way of saying slope. So that's s of b minus s of a all over b minus a. And then we have our instantaneous velocity, remember, is limit as t goes to infinity of the rate of change. Well, what is that? Remember, that's derivative. Okay, s of t stands for position function. Then we have the derivative of s of t is going to be v of t, or our velocity function. And remember, that is the units on that is going to be some distance that we're talking about over some time unit. The absolute value of velocity is going to be what we call speed. Think of your speedometer. And the derivative of velocity, which remember is the second derivative of position, is going to be our acceleration function. And I want to just remember or highlight a few things for those of you that might not be in physics. So velocity. Velocity is a vector. It gives us distance. I'm sorry, it doesn't give us distance. It gives us our direction. And then it gives us our speed. And so what that means is when we have a positive velocity, down here, when I have a positive velocity, I am moving right or up. So meaning, think about if you're on a number line, if you're moving to the right, v of t is greater than 0. If you're moving left, v of t is less than 0. And that makes sense because I think of 0, and then you have numbers to the right are positive, numbers to the left are negative. Okay, our first example. Okay, so we have a tennis ball is dropped from a height of 150 feet. The ball's height, s, at time t, is measured by that position function, where s is measured in feet and t is measured in seconds. Now, I just want to give you a heads up. The book, they have you fill in certain pieces of this equation. They give you a more general equation. So if you're in physics, they're giving you an equation that is similar to one you're going to find in physics. I'm always going to give you what the position function is, because I don't need you to memorize the physics formulas. I need you to know how to do the calculus with those formulas. Anyway, okay, so we have the average velocity on an interval from 1 to 2 indicate the units of measure. So average velocity, so that is s of 2 minus s of 1 over 2 minus 1. S of 2 is 86. S of 1 is 134. All over 1. We have negative 48 feet per second. So the instantaneous velocity, now that is derivative. And this is at 1.2. I edited the problem, so 1.2 seconds. So instantaneous, well, that's derivative. So I have the derivative function, which is negative 32t. I have to find s prime of 1.2. I plug in 1.2, and I get negative 38.4 feet per second. Unit of distance, feet, over second. Feet, unit of distance, over a unit of time. And then is there a time interval from 1 to 2 where the average velocity, so my average velocity, negative 48, equals the instantaneous velocity, negative 32t. So I solve that, and I get t to be 1.5 seconds. Okay, our second example. A diver jumps from a platform diving board that is 32 feet above the water. The initial velocity of the diver is 16 feet per second. The diver's position, s, at any time, t, is given by this formula. Again, the book is going to give you a very different formula. I'm always going to give you this position formula, just so that you know. Initial, so this is s sub 0 in that formula in the book. Your initial position, and then that is v sub 0, your initial velocity. For those of you that aren't in physics that might not be familiar with the formula. Okay, so I have to figure out when the diver hits the water. So his distance above the water is 0 when he hits the water. So I set this equation equal to 0. This is one of my favorite problems when I used to teach Algebra 2 trig. I factor out the 16. And then I factor that, and that factors to t minus 2, t plus 1. So I have t equals 2 and negative 1. We do not have a DeLorean. We are not Michael J. Fox. We do not go back in time. So we can ignore the negative. So at t equals 2, it takes him 2 seconds to reach our water. What is the diver's velocity at impact? Okay, so we have to find our velocity function. Negative 32t plus 16. I plug in 2. So for my velocity, just remember, I took the derivative position. I plug in 2. And I get negative 48 feet per second. Okay, third example. A particle moves along a line so that its position at any time t greater than 0 is given by that function, where s is measured in meters and t is measured in seconds. Find the equations of the velocity and acceleration functions. I don't know if that's proper English, but remember our derivative of our position function is our velocity function, and that is 3t squared minus 18t plus 24. And then our second derivative of position, which is the derivative of velocity, equals our acceleration function. You don't have to write all of that each time. I'm just doing it this one time, which is 6t minus 18. Okay, find when the particle is moving left and moving right. So first I have to set my velocity function equal to 0. Notice in my velocity function, each one of those coefficient is a factor of 3. So I'm going to factor out that 3. Then we're going to go through and factor and I'm going to factor correctly. Okay, so then I have now t equals 4 and t equals 2. So I set my velocity equal to 0. That's where I'm stopped. And then those become what we call critical points. So on a little number line, we're going to talk about our velocity function, and we're going to find numbers on each one of those intervals, and we're going to determine what the sign of our velocity function is. Because remember, if I'm moving left, v of t is less than 0. If I'm moving right, v of t is greater than 0, or positive. So if I plug in something between 0 and 2, I have an endpoint of 0 because it says for t greater than 0, greater than or equal to 0. So if I plug in 1 there, plug in 1 into our velocity function, what I do is I plug it into this function here. I know it's set equal to 0, but I look at it like it is the velocity function because that's easier for me to tell. So 0 to 2, I end up being positive. And I plug in a number between 2 and 4. So like 3. When I plug in 3, I'm negative. And then something greater than 4, I'm positive. So we are moving left from 2 to 4. We're moving right from 0 to 2 and 4 to infinity. And then what is the particle's velocity when the acceleration is 0? Particle's velocity when the acceleration is 0. Okay, so I need to set my acceleration function, which we have. Our acceleration function is 6t minus 18. I set that equal to 0. Okay, so t equals 3. So I need to know what v of t is. v of 3 is. So v of 3, I'm going to plug into this equation here that I have highlighted. And if I plug in correctly, I was looking at the t. Just because it's the same function, and that's easier for me to find. 3 minus 4 is a negative 1. 3 minus 2 is a positive 1. So I have negative 3, and let's throw some units on there, meters per second. So that's my video on rate of change. Basically what that is, rate of change, we're going to be dealing a lot with different particle motions. Thanks for watching.